In today's video, I want to talk about how to calculate the non-dissociated adiabatic flame temperature. I'll go through an example with the classic fuel, which is methane. I first encountered the flame temperature many years ago in a first semester thermo course. I guess it was about 3 weeks into the course, and the problem was near the end of a small number of homework problems in a book by Bruce Methane, which is titled Elementary Chemical Thermodynamics. To be exact, the problem that he had is the one you see here. It says, find the maximum temperature that might be attained in an acetylene torch flame which burns at constant pressure according to this written reaction, so which we have as acetylene, 3 halves oxygen, CO2, and water. It went on to say, assume that the reaction goes to completion, that the reagents are initially at 300 K, and that there's no energy loss from the flame. Well, at that time, the students and I were fairly clueless about how to approach that problem. And in truth, that's not really today's example, but it is in line with our interest. Once you've mastered our methane example, perhaps you'll be inclined to do this one for yourself. So what problem are we going to do? Let's write it out and carefully look at it. Our problem says, calculate the adiabatic flame temperature in air at constant pressure, assuming the following balanced equation. I want to point out that there's a separate video on how to balance combustion equations with air. If you need to look at that, there's a link in the notes. So this equation says methane plus 2 moles of air, that's oxygen, and 3.76 nitrogen. You'll remember 3.76 comes from 79 over 21, and that's simply 79% nitrogen, 21% oxygen. So that goes to CO2, 2 waters, and that is 2 moles times 3.76 nitrogen, so 7.52 moles of nitrogen. Assume that the reaction goes to completion and that the starting temperature is 300 K. Notice that the nitrogen appears on both sides of the equation and in the same amounts. We can't just remove it from consideration because it's inside the adiabatic combustor and it's one of the molecules that will heat up. It's important to write the reaction because the flame temperature depends on exactly what molecules are present on the product side, this side, at equilibrium. Indeed, the reaction, the way it's written here, doesn't actually occur. What really happens is that when the temperature gets above about 1,000 degrees, we start getting dissociation of the CO2, dissociation of the water, and association of the nitrogen. For example, these reactions, water going to hydrogen and oxygen, and these other 2 reactions start to occur, and that increases the number of species on the right-hand side, and that drastically could change, actually does change by many hundreds of degrees, the final temperature, because this just isn't the reaction that finally occurs. So I guess the point is that any calculated answer is only as good as the chemical reaction that you've written down. Also, note that the reaction is adiabatic. That means that no heat escapes. What that comes down to is to say that this flame temperature that we're going to calculate is the theoretical maximum. Now, the steps to calculating a flame temperature, there are 4. And I'm not going to write them for you, but I'll at least tell you what they are. Step 1 is to write the equation down. We wrote the equation down right here, so we've got step 1 taken care of. It has to be balanced. Step 2 is to apply conservation of energy. This is an awfully important step. It's as simple as what I show here. The delta H of the reactants is equal to the delta H of the products. The trick, which we're going to go through, is how you go about writing math for the delta H of the reactants and the delta H of the products. It's easy, but once you do it, you're all but done. So that's step 2 is to write that conservation equation. Step 3 then is to go find the details of that equation. In other words, let's find some numbers to put in. And then step 4 is just to pick a calculation method and compute. Let's look at steps 2 and 3. Here I've written the enthalpies for reactants and products. I know this looks complicated, but let's go through it. The red elements represent the reactants and blue the products. If we solve this equation for T2, that is the flame temperature. You see T2 appears here, here, and there. All right. We see three sets of parentheses on each side of the equal sign. 1, 2, 3, 1, 2, 3. Why? If we look at the balanced equation, we can see that it also can be arranged as three terms on each side of the equal sign. The parentheses containing the species name, here CH4 or here O2, that parentheses only serves to identify which chemical entity is being addressed, and it's not part of the math. Let's break apart the first term, the one here. This is for methane. Inside the parentheses, there's two terms, one with an integral sign and one without. You can recognize both terms. The one without the integral is the heat of formation of methane. It's the chemical heat contained within methane as a consequence of its existence. You see this same term in each of the other parentheses. So we have the heat of formation of the reactants there, 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 and then the heat of formation of the products there, there, and there on either side of the equals. The integral term is known as the sensible heat of methane. And you may recall that the sensible heat is written as the change in heat is the integral from an initial temperature to a final temperature, Cp dt. The reason we do this is because usually the Cp, the specific heat, is dependent on temperature. And in the case of a flame, it's very, very dependent on temperature. So typically, you can't just take it outside the integral. Our sensible heat term is just the heat needed to raise the temperature of methane, or whichever one is being referenced, from some reference state to the starting temperature of the reactants. In our problem, we said, and notice the starting temperature of the reactants right here, T1. In our problem, we said that temperature would be 300 degrees K. Note too that NIST and ISO and much of the rest of the world uses 298.15 K as the reference temperature. Had our problem said 298.15 K, then these integrals, that one, this one, would have evaluated to 0. As it is, they're going to be very nearly 0. The reactant side is state 1 before the reaction, and so we integrate to T1. The product side is state 2 after the reaction, and so we integrate to T2. T2 at state 2 is the flame temperature. In our 4 steps for identifying the flame temperature, step 3 was to identify the needed data. I'm going to do that by building a table. All right, so in this table, I've identified the species. We have methane, oxygen, nitrogen, that's reactants. And then on the product side, we have CO2, water, and nitrogen again. I've also identified the heats of formation, minus 74.6. I looked that up. I'm going to give that a variable name, A prime, which I'll explain in a minute. Heat of formation for oxygen, well, that's going to be 0 because that's the definition of a pure element. Same with nitrogen, it's going to be 0. Heat of formation of CO2 is minus 394. Heat of formation of water is minus 242. Heat of formation of nitrogen again is 0. Notice each time I've given them a new letter, A, B, C, D, E, F, and there's a little prime by them. The little prime indicates it's a heat of formation rather than a sensible heat. Now in the sensible heat column, these aren't exactly numbers yet. We're going to work hard at turning them into numbers, but they're not there yet. So they're still written as the integral signs for each of the species. And then there's a coefficient. There's a coefficient, and those are the coefficients up here. So 1 is for the parentheses on methane, 2 is for the parentheses on oxygen, etc. And each of these sensible terms the term itself, is going to be identified by a single letter, A, B, C, D, E, or F. So this is A right here, and this is A prime, this is B prime, etc. So what I want to do is manipulate these terms with algebra. So what I've done is I took, this is this set of equations, but now it's written down in terms of the A's and B's. So I have the first parentheses with A and A prime, the second parentheses, the third parentheses. I've kept up with the coefficients. So I've actually just written the above equation in a form that's a little bit easier to manipulate, basically because I'm lazy. And let's go to the, so the next thing I did was to simply remove the parentheses and expand everything out so I keep up with the coefficients. And then in the next one, I am going to take the prime terms, that would be the heats of formation, and move them all over to the right-hand side. So everywhere up here where you see a prime term, I've put the prime terms on the right-hand side right here, and of course when you move them to the right they become negative, so it's negative all of these prime terms. The other prime terms that were already on the right-hand side stayed, and then I've taken the sensible terms that were on the right-hand side here, that would be D, 2E, and the F term, and I've moved those, given them negative signs, and moved them over to this other side. Now what I want to do is take values from the table and start filling things in. Well, I don't have any values for the sensible terms, and the sensible terms are all on the left, so I'll ignore that for a moment. But I do have values for all of the heats of formation. So A prime, for instance, is minus 74.6, and then there's a 2 B prime, and that B prime is 0, then the next one is 0, and then we've got the CO2 term and its coefficient of 1, and then the water term and its coefficient of 2, and then a nitrogen term and its coefficient of 2 times 3.76. So finally, I'll collect together all the terms and do the arithmetic and sum everything up, and I'll get this term, which is basically the enthalpy of the reaction. It's the products minus the reactants. And in combustion chemistry, it's almost always called Q. It's sometimes given the opposite sign from what you see here, but if you want this equation to work, you have to keep the correct sign. Later you'll see it gets switched because the signs on the other side will all be negative also. But this is 803.8 kilojoules per mole, and that is our enthalpy of the reaction. All right, now returning to the table, I need to find sensible heats for these reactants, these three. Notice that when we wrote it into the table, while I had mentioned that these are almost 0, well, they're not quite 0, and potentially we could integrate that if we had any information. As it turns out, we don't actually have to integrate it because I can find a spot in a table where it's been done for me. So I'm going to try to show you that. Here I've gone to the NIST Webbook, and I'm going to enter the name methane. All right, and then I'm just going to enter methane and let it go at that. All right, so here it switched me over to methane. And we're going to come down here and we're going to look at the gas phase thermochemistry data. There you can see the heat of formation. That's a nice place to find that. But then we're going to scroll on down and see if we can't find, there's some CP values, but it'd really be nice to find even better than that. And I can, if I look at this table right here, scroll on down a little bit. Okay, so here's temperature and then heat capacity in joules per mole K. Ignore entropy and Gibbs. But let's look over here. This is the reference temperature for enthalpy, 298.15, and they've already subtracted off. In other words, they've done the integration of heat capacity and temperature, and this is the integration result right here. So it's at temperature of 300 degrees. Wow, it's convenient that they have 300. They've subtracted off their reference temperature and given me what the value is. So the number that I'm looking for my sensible heat right there is 0.07. In terms of the flame temperature, there are other numbers down here, as you can see. We can use those. We'll get to that later, but right at the moment, we're interested in this 0.07. I'll put the URL for that NIST data in the notes. Similarly, you can find data at the Webbook for oxygen and for nitrogen and, frankly, just about anything else you want. Sometimes you can only find the CP data. You can't actually find those enthalpies, and then you have to do the integrations yourself. In order to do an integration from the CP data, you usually have to take the data points and copy them into some other program and fit them with, say, a polynomial, and then you can integrate that polynomial. So here's our table with the sensible data that we found filled in for the reactants. Down here, I've shown the equation. We've whittled this down quite a bit. These are the reactants minus the products, and then over here is the Q value, heat of the enthalpy of formations. Still, T2 is what we want to find, so just integrating these three terms is not going to work out. Here's a list of possible ways to a solution. Number one is intelligently pick a single average heat capacity for each of the unknown species. You can pick from the Webbook table. The math gets obviously easy since CP becomes a constant, and you can just solve for T2. T0 is still 298.15. Clearly, the result will be weak since you know that heat capacity varies with T2. All right, a second way is to find a table of heat capacity versus temperature values and fit that to a polynomial. That polynomial can then be algebraically integrated. If you choose a low-order polynomial, like order 1, 2, or 3, 1 being a straight line, you might be able to solve for T2. Unfortunately, low-order polynomials yield a very poor fit to the data, and you might as well resort to method 1. All right, method 3 is to do the same thing as method 2, but use Newton's method to solve the equations, thereby allowing you to use a higher order polynomial that actually fits well. This is basically a lot of work. It's going to involve some programming, but given the quality of the answer, it's a good approach when all of the dissociation reactions have already been included into the equation. This numerical solution is what the sophisticated online solvers use. Method 4 is the one I'm going to show here. We want to find a table that has already done the integrals for you at many different temperatures. That's the table that we referenced above with carbon dioxide, oxygen, and nitrogen. Then we want to fit a polynomial to the table data so that we can quickly compute each integral. Now, if you notice this equation that I've written down here, it's the same as this equation up here. I've just taken the three constants and moved them over to the right-hand side. When I do that, I came up with minus 804.346. We said those constants were nearly zero, and they are. But you'll notice that leaves integrals on this left-hand side, and if I can guess a value for T2, then it's pretty trivial to perform these integrals, especially if the integral has already been performed for me and all I'm having to do is take a function and get a value for it. That would allow me to guess a value for T2 and see if it matches the value on the right-hand side. Okay, here I'm showing a solution using a program called Geogebra, which is freely available online. Anybody can get at it. I have imported data from the Webbook I've imported data from oxygen. We're not going to use that. But I've imported data for CO2, water, and nitrogen. In each case, it's a list of temperatures and a list of enthalpies minus the standardized enthalpy or the reference point. So they've already done the integration for me. I'm not having to use heat capacities directly. So what I want to do is I want to plot this data and fit a point to it, and fit a line to it, so I have an equation, and so I can quickly generate any temperature that I would like. Okay, so here, and you'll have to learn how to use Geogebra to do this, although I have to tell you it's really quick. Here I've shown the 3 points. So my red points are for CO2, my blue line is for water, and my green lines are for nitrogen. And these are those data points that I was just showing you, which came from that web book. Now, I fit the line to it in the range of 298.15 degrees K all the way out to 6,000, only because I had data all the way out to 6,000. At this point, I don't anticipate needing anything much above 2,500 or so. So I'm going to start then with a temperature of 800 degrees, and I'm going to start changing it. You can see it if I punch in 800 degrees, and I look at these, and I look at, this is my integral, my first integral, my second integral multiplied by 2, of course, my third integral multiplied by its coefficient, and I'm going to compare it to that 804.346 that we had. That's that Q minus reactants. So 800 is clearly too low, and so let's raise our temperature up some. If I raise my temperature up to 2,300, I'm getting closer. That's definitely better. If I went to 2,400, let's see what would happen. If I went to 2,400, okay, now my temperature is too high, so now I have to start bringing it down, see if I can find it. So let's try 2,340. How close is that? That's 806. That's just a little bit high. Let's try 2,335. That's 804.67. You can see that even though I'm essentially guessing the answer, one can intelligently guess quite quickly when you have tools like this. All right, well, that's all I have for the flame temperature. Good luck. Hope you understood it. You can ask questions if you need to. Thank you.